Alors, what's on the menu for today? Monotonic divergent series of triangular numbers. So today we're going to prove 7 proofs that the sum of the monotonic divergent series of triangular numbers 1 plus 3 plus 6 plus 10 plus 15 etc. is -1 over 24. Proof number 1, generating function. So let GF, G and F for generating function, be the ordinary generating function for the monotonic divergent series of triangular numbers. So the formula is as follows. The generating function, the ordinary one, is 1 over 1 minus x to the cube, which expands in a form of 1 plus 3x plus 6x squared plus 10x cubed plus 15x to the 4th, etc., etc. So if we evaluate the above function at x equal 1, we obtain gf of x at x equal 1 is equal to 1 plus 3 plus 6 plus 10 plus 15 plus 21, etc. You can see it from here, which are the triangular number that we are after. So that expression 1 over 1 minus x to the cube, if we evaluate it with x equal 1, we have of course 1 over 1 minus 1 to the cube, which is 1 over 0 to the cube, 1 over the 0, which is infinity. So applying the fundamental theorem of divergent series of integers, we conclude that the monotonic divergent series of triangular number is unstable. Why unstable? Because when we evaluate it using the ordinary generating function at the value of x generating the series, we do not get a finite value. We get something over 0 at the denominator, which is infinite, and that tells us that the series is unstable. In other words, when we shift that series to the right by inserting leading zeros, or when we space the series equitably spaced with zeros in between, we will get a different value. That's what it means. So therefore, we cannot determine the sum of this divergent series by evaluating its ordinary generating function with the value generating the series at x equal 1. Therefore, it is not a proof. Proof number 2, direct calculation. So let's write down the monotonic divergent series of squares. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, etc. What is equal to? Let's open the toolbox. The sum, the sigma from n equal 1 to infinity of the squares is equal to 0. That value is 0. We showed it on a previous video. It corresponds to the value of the Riemann zeta function at -2. Or to B3, which is the fourth Bernoulli number, also equal to 0. So we plug in the 0 here. Then the other divergent series that we need is the monotonic divergent series of natural number, 1 plus 2 plus 3 plus 4, etc. And the sum of this one, we have seen it as well, you know it, it's -1 over 12. So we plug that value as well. So when we have those two divergent series with their sum, 0 and -1 over 12, we can sum those two divergent series. So I'm using a plus with a circle around it to make a big difference between the sum of the addition of two divergent series compared to the plus sign, which is making up the series between the terms. So now we sum that. What do we get? We get those numbers, again, column by column as usual. 1 plus 1 is equal to 2. 4 plus 2 is equal to 6, 9 plus 3 equal to 12, 16 plus 4 equal to 20, 25 plus 5, 30, and the last one, 42. So if we do that on the left-hand side, then of course we must do the same on the right-hand side of the equal sign that we have here. 0 plus -1 over 12 obviously gives us -1 over 12. So that monotonic divergent series corresponds to the, it's called the oblong or pronic numbers. So those numbers, oblong or pronic, are to the triangular numbers what the even numbers are to the natural numbers. In other words, it's times 2. So, and because of that, so let's divide by 2 or multiply by 1/2 that divergent series, and we get 1 plus 3 plus 6 plus 10 plus 15 plus 21, half of those numbers. And then of course, if we multiply by 1/2 on the left-hand side of the equal sign here, we must do the same on the right-hand side, which of course gives us 1 over 24. So if we rewrite the above in sigma notation, what do we get? So the sum from n equal 1 to infinity of the triangular numbers, which are those ones that we are after. This is a divergent series, 1 plus 3 plus 6 plus 10 plus 15, monotonic divergent series of triangular numbers, it's equal to, like we have done it here, the 1/2, which is here, 1/2 comes here, of n times n plus 1. In other words, n squared that we have here plus n that we have there. Here it is. Now we use a linearity. The sigma of the sum is equal to the sum of the sigma, the sum of a sum. That one, we've seen it, it's a 0, which is here. We plug it in. Next one is negative 1/12. We have it here. We plug it in. Let's not forget the 1/2. And 1/2 of 0 negative minus 1/12 is, of course, negative 1/24. That is exactly the calculation that we have done here on the right-hand side. And that is the correct result. So that direct calculation gives us the sum of the triangular number of the monotonic divergent series of triangular numbers starting from 1, which is equal to negative 1/24. Let's erase the board. In terms of generating function, we have 1/2 of 1 plus x over 1 minus x cubed plus 1 over 1 minus x squared. So if you multiply the right-hand side fraction by 1 minus x, you will have 1 minus x cubed at the denominator, what we need, and on the numerator, we will get 1 plus x plus 1 minus x. Of course, the x's will simplify, 1 plus 1 equal 2 will simplify, and we are left with 1 over 1 minus x to the cube, which we have seen on the first proof that it is the ordinary generating function of the monotonic divergent series of triangular numbers. So we can see here that the monotonic divergent series of square numbers plus the monotonic divergent series of natural numbers multiplied by 1/2, so in other words, the arithmetic average of those two, is equal to the monotonic divergent series of triangular numbers, what we have seen on the previous board. All right. Direct calculation. Another example of direct calculation using the sigma notation, we can write it like that. Sum from n equal 1 to infinity of the triangular numbers n plus 1/2 can be written as the half difference, so 1/2 of the sum from n equal to, not 1, n equal to infinity of the squares, minus the sum from n equal to infinity of the natural number. So the sum of the squares minus the sum of the natural number, but not starting from 1, starting from 2. I'll let you verify that for yourself. Then what do we get here? Let's open the toolbox. We need some result. The sum from n equal to of the squares is equal to negative 2/3. And the sum from n equal to of the natural number is equal to negative 7/12. So let's plug that. Negative 2/3, negative 7/12. It gives us 1/2 of negative 2/3, minus become plus 7/12. So multiplied by 4, give us negative 8/12 plus 7, so it's negative 1/12 times 1/2 equal negative 1/24, and that is the correct result. So it's another example of direct calculation that we can use to determine the sum from n equal 1 of the monotonic divergent series of triangular number. Again, we get to negative 1/24. All right. Proof number 4, intercept functions. So we will follow the same steps that we have followed in the previous videos. So step number 1, we calculate the partial sums or the sequence of partial sums. So let's write down the series, a monotonic divergent series of triangular numbers that we are after, 1 plus 3 plus 6 plus 10 plus 15 plus 21, etc. The first term of the series will be equal to the first term of the sequence of partial sum, so 1 equal 1. Then 1 plus 3 equal 4, the second term of the sequence of partial sum, plus 6 equal 10, the third term, plus 10 equal 20, plus 15 equal 35, plus 21 equal 56. So that sequence of partial sums, 1, 4, 10, 20, 35, 56, it's called tetrahedral numbers or triangular pyramidal numbers. So if we express the partial sum S uppercase n for sum, uppercase n, that's the index that I'm using for the sequence of partial sum, lowercase n for the sequence of the index of the series. So express the partial sum S of n as a closed form expression. That's important, must be a closed form expression. So S of n, which is the sum from n equal 1 to uppercase n of n plus 1 over 2, which is the expression of triangular number. Let's open the toolbox. What is that? It's expressed as n times n plus 1 times n plus 2 over 6. That is the expression for what we call the tetrahedral numbers, or triangular pyramidal numbers. So let's take that expression, we plug it in, here it is. And in that expression, of course, n, which is the partial sum from lowercase n equal 1 to uppercase n, is a natural number. So step 3a, calculate the intercept point h of n as a half sum, h for half sum, of two consecutive partial sums. So again, h of n, uppercase n, is equal to s of at n minus 1 plus s, partial sum at n, divided by 2. So the first term will be, we just use that expression, and then we replace n by n minus 1. So n becomes n minus 1, n plus 1 becomes n plus 2 become n plus 1. And of course 6 at the denominator becomes 12 because we divide by 2. The other one is straightforward, it's the same thing divided by 2, so 6 becomes 12 at the denominator. And then when we sum those two, obviously we have a fraction over 12, and the numerator becomes n times n plus 1 times 2n plus 1. You can develop those two terms and add them, you will see, that's what we get. So we assume S0, the partial sum at 0 equals 0. In other words, we implicitly assume a 0 here before the sequence starts. Before it starts, there is nothing, we make it equal to 0. Step 3b, express a continuous intercept function h of x by replacing uppercase n with x. Uppercase n, of course, it's a natural number, x will be the real number from the real line. So here is the expression, we replace the uppercase n, our index for the partial sum, partial sequence, with x being a real number, and that is the expression of the continuous intercept function h of x. Let's scroll down to the board, more space. Step number 4, evaluate h of x where x equals 0. So h of 0 equals 0. You've seen the expression on the previous, at the bottom of the previous board, and therefore the sum from n equal 1 of n plus 1 over 2, which is that divergent series, monotonic divergent series of triangular number, is equal to the value of the intercept at 0 after projection on Q, the set of rational numbers, which is, of course, 0 is already a rational, so it's equal to 0. Is this correct? Nope, that's not the correct answer. We have seen it already in the previous 2 or 3 proofs, that it's negative 1 over 24. So where did we go wrong here? In that case, we need the adjusted intercept for the monotonic divergent series of triangular number. And that adjusted intercept, h sub a of x, can be expressed as negative 1 over 24 plus x squared times 2x plus 3 over 12. So that is a correct formula for the adjusted intercept function that we need. And once we got that formula, we evaluate it at x equals 0. So it's relatively straightforward, obviously. Negative 1 over 24 plus 0 over 12, which disappears. So it's negative 1 over 24. And finally, the sum from n equal 1 to infinity of the triangular numbers, which is that those numbers, is equal to the adjusted intercept at 0 projected on Q. But again, that is already a rational, so projecting won't make a difference, but we need to project on a set of rational number, and it's equal to, obviously, negative 1 over 24, which is the correct answer. So that proof is correct, it's valid, but it's incomplete because we haven't proven where that adjusted intercept function is coming from. So because of that, it does not qualify here as a proof until and unless we prove that expression, where is it coming from. We will do that on another video. All right. Number 5, partial sum integral, PSI. So we will use that method to calculate the sum of the monotonic divergent series of triangular numbers like we have done on the previous videos. Same steps. Step number 1, calculate the partial sums. So we have done it already. We know the partial sum of the monotonic divergent series of triangular numbers are the tetrahedral numbers or triangular pyramidal number 1, 4, 10, 20, 35, 56. Step 2a, express the partial sum S of n as a closed form expression. So S of n equal the sum from n equal 1 to uppercase n of the triangular numbers, which if we open the toolbox, we've seen it on the previous board, it's the sum of n equal 1 to uppercase n of the triangular numbers is expressed as a closed form as n times n plus 1 times n plus 2 over 6. So we can plug that in. Here it is, n being a natural number, obviously. Then we express a continuous partial sum S of x. So in that case, Sn is n times n plus 1 times n plus 2 over 6. We replace all the discrete variable with x being on a real line. Then we can calculate the PSI. So the PSI, by definition, the partial sum integral, is the integral from negative 1 to 0 S of x, which is a continuous partial sum dx. So let's plug it in. So we pass the 1 over 6 in front. So 1 over 6 integral from negative 1 to 0 x times x plus 1 times x plus 2, the expression that we have here, is equal to, instead of to have a triple product, let's have rather a triple sum. So we develop all of that. It gives us x cubed plus 3x squared plus 2x. And then I'm sure you know that the integral, or in that case indefinite integral of x to the n is x to the n plus 1 over n plus 1 plus a constant. The constant, we don't bother here with it because we have born of integration, negative 1 and 0, and it will cancel the constant out, so no material impact here. So let's use that formula. X cubed become x to the 4th over 4, 3x squared can be integrated as x cubed, and 2x as x squared. So now it's easy. If we evaluate that at 0, everything disappears. It's all 0 values. So we just have to evaluate at negative 1. Negative 1 over 6 of that value as negative 1, which is 1/4. This one, it's the exponent is an odd number, so it will be negative 1. And that one is an even number, so it will be plus 1. Of course, the plus 1, negative 1 will simplify each other out, and we are left of negative 1 over 6 of a quarter, which is, of course, negative 1 over 24. So if we write it in sigma notation, the sum from n equal 1 to infinity of the triangular numbers is equal to the PSI that we just calculated after projection on Q. So here, negative 1 over 24 is already a rational number, so it doesn't make a difference. But keep in mind, you need to project on Q. And it's equal, obviously, to negative 1 over 24, which is a correct result. So that continuous function, if we plot it, let's have a look. That's how it looks. You can see that nice curve there. It's a third degree polynomial. And then the partial sum integral obviously corresponds to the integral between negative 1 here, that point, and 0. So as you can see, the whole curve is under the horizontal axis. So it's all of that is highlighted in red to remind us that it's a negative value. And the surface of this area highlighted in red, which is below the horizontal axis, therefore all negative, is equal to that value that we have here. It corresponds to that. So visually, that's where the negative 1 over 24 comes from that area. All right. Proof number 6, Ramanujan summation. So like on the previous video, let's apply Srini's summation method to this monotonic divergent series of triangular numbers. So the sigma, the sum from n equal 1 to infinity of a function f of n is equal to negative the value of this function evaluated at 0, or negative 1/2 of it, minus the sum from m equal 1 to infinity of the even Bernoulli number b2m over 2m factorial times the 2m minus 1 derivative of the function evaluated at 0. So where b2m, like I said, 2mth, or actually 2m plus 1 Bernoulli number in a context of b1 equal plus 1/2. Always, when you use a Bernoulli number, always know in which context you are, b1 equal negative 1/2 or plus 1/2. So in that case, it's plus 1/2. So of course, we're going to set f of n being n plus 1 over 2, which corresponds to the triangular number for any value of n greater or equal even to 0. We need the value at 0 here. So that is f of n. At 0, obviously, it will become 0. 0 times 1 over 2. The derivative of f for n, so n squared over 2 will become n over 2 becomes 1/2, so n plus 1/2. The value at 0 is of course 1/2. The second derivative, 1/2 is a constant, disappear, n becomes 1, we have 1, therefore the value at 0 is equal to 1, it's a constant. And we can generalize from there on, it's a constant, so anything after that, the third derivative, fourth, fifth, etc., will all be equal to 0. Once you reach a constant, it doesn't get any better. Everything becomes 0, and then the value of that 0 function will always be 0 at 0, evaluated at 0. So once we have done that, we can now plug all of that into Ramanujan's summation formula. So that is valid for any value of m greater or equal to 2. You can see not 1, because for 1 it's here, it's n plus 1/2, sorry, on that side, and 1/2 on the right hand side. So it's equal uniformly to 0 from any other value n greater or equal to 2. Which means that infinite sum that we have of derivative of f with a factor in front, the even Bernoulli number divided by 2m factorial, that infinite sum will only have one term, because from m equal 2 onwards, they are all equal to 0. So let's write it down. We obtain the sum from n equal 1 to infinity of f of n is equal to the sum of n equal 1 to infinity of the triangular number, by definition of the function that we have chosen, which is equal to negative 1/2 of f evaluated at 0 minus b2 over 2 factorial of the first derivative f prime at 0. Again, only one term on that infinite sum, because for every value of m greater or equal to 2, it's uniformly equal to 0. Not even the value of that 2m minus 1 derivative of f is equal to 0 at 0, but it's equal to uniformly to 0. So let's plug that in. Minus f0 over 2 is equal to 0. F prime at 0 is equal to 1/2. We have it here. So here we're gone. We are left with minus b2 over 4. In other words, 2 factorial is equal to 2 multiplied by 1/2. It's 1/4. So negative b2 over 4. Let's open toolbox. What is b2 equal to? b2, the third Bernoulli number, is equal to 1/6. We plug that in. 1/6 multiplied by negative 1/4, it gives us negative 1 over 24. Here it is. Ramanujan summation works well. It gives us the value, or the sum, of the monotonic divergent series of triangular number, confirmed to be negative 1 over 24. Proof number 7. Abel-Plana summation. So let us apply Abel-Plana's summation method for monotonic divergent series. Here it is. So the sum from n equal 1 of f of n, it starts like Ramanujan's formula, negative 1/2 of f evaluated at 0, but then we followed by a complex integral. So plus I being the square root of negative 1, of the integral from 0 to plus infinity of f of it minus f of negative it over e to the 2 pi t negative 1 minus 1 dt. So using f of s equal ss plus 1 over 2, for s being a complex variable, we have f of 0 equals 0, f of it times it plus 1 over 2, which can be simplified as I square being negative 1, so negative t square plus it over 2. We do the same thing for negative it times negative it plus 1. We develop, so it gives us a negative t square, or I square t square, so negative t square minus it over 2. So if we plug those two values here on the numerator of what is inside the integral, what do we get? So first, f of 0 equals 0, so we are left with nothing here, that's gone, plus I times the sum of those two, so the it over 2 will simplify, will double with the negative it over 2 because of the negative sign, so we have two of them, so we are left with it, where the negative t square over 2 will simplify with the other one because of the negative side, and negative t square over 2 plus t square over 2 cancel each other out, so we left only with it. So that one is gone. So how do we move from here to there? So I in front give a I square of course is negative 1, so we have the negative 1 here. Then what I've done is I added 2 pi with a t here, so multiply by 2 pi, and also I did 2 pi in front of the derivative and pass it inside. So the derivative of 2 pi t is the same as the derivative of 2 pi times dt. So because I've multiplied by 2 pi here and another 2 pi, I multiply by 4 pi square, and that's why I divide by 1 over 4 pi square to balance it out. So why do I do that? Simply because we want to use a Bose integral, which is defined as the integral from 0 to plus infinity of u in a u world, u to the s minus 1 over e to the u minus 1. So now if we replace that with the change of variable u equal 2 pi t, so you can see we just rewrite the same thing, 2 pi t to the s minus 1 as an exponent over e to the 2 pi t minus 1 d to the 2 pi t. And now when you compare those two expressions, you can see they are the same for the value for the exponent be equal to 1. In other words, for s equal to 2, s minus 1 equal to 1. And that Bose integral, we know that it's equal to gamma of s, zeta of s. The gamma function evaluated at s times the Riemann zeta function evaluated at s. So which value the s of s do we need here? We need the exponent to be equal to 1. We can see it's equal to 1 here. Therefore, s is equal to 2. So if we use that formula s equal to 2, it gives us gamma at 2 times Riemann zeta function at 2. Let's not forget the constant in front, negative 1 over 4 pi square. So now we need those values. Let's open the toolbox. Gamma at 2. Gamma at 2, gamma of n is n minus 1 factorial. So gamma at 2 is 1 factorial. 1 factorial obviously is equal to 1. And the Riemann zeta function at 2, it's the Basel constant, pi square over 6, that Euler famously found in the first half of the 18th centuries, made him famous for that. So I'm calling that constant the Basel constant, pi square over 6. So now we have our two values, we plug it here. First one is 1, the second one is pi square over 6. We can simplify the pi square or the numerator, and that one is at the denominator, we simplify, and what are we left with? Negative 1 quarter of 1 over 6, which of course gives us negative 1 over 24, which is the correct result. All right. So here we get as well to the correct result, negative 1 over 24 for the monotonic, the sum of the monotonic divergent series of triangular number using the Abel-Plana summation method and the Bose integral as a shortcut for the calculation here. Cool. Proof number 8, Riemann zeta function. So the Riemann zeta function zeta, that's the Greek letter zeta of s, is defined as zeta of s, the sum from n equal 1 to infinity of 1 over n to the s. In that case, s is a complex variable on a complex plane. So the sum of the monotonic divergent series of the triangular number, starting from 1, 1 plus 3 plus 6 plus 10, etc., is equal to the arithmetic average of the Riemann zeta function, zeta of s, evaluated at or with s equal minus 1 and s equal minus 2. Let's have a look. Here it is. So the trick here is simple, is to express n squared as 1 over n to the minus 2. And likewise to express n as 1 over n to the minus 1. Why do we do that? Because when we compare that expression with the expression of zeta, we can see s equal negative 2 will give us that one, and then s equal negative 1 will give us this one. So we can write it is therefore equal to 1/2 of the Riemann zeta function evaluated at negative 2 plus the same Riemann zeta function evaluated at negative 1. So in other words, like I'm saying above, it's the arithmetic average of those two values. Let's open the toolbox. We need those values. The Riemann zeta function as negative 1, it's negative 1 over 12. You know that. And then the Riemann zeta function at negative 2 is 0. It corresponds to 7/3 of B3. B3, the third or actually fourth Bernoulli number equal to 0. So we plug those values. Zeta at minus 2 equals 0, zeta at minus 1 equals negative 1/2, and of course that one will go out, and we are left with 1/2 of negative 1 over 12, which of course is negative 1 over 24, which is the correct result. So again, it's a one-line proof using the Riemann zeta function. Proof number 9, Dirichlet eta function. So the Dirichlet eta function, eta of s, it's the n with a long n leg, is defined as eta of s at the sum from n equal 1 to infinity of -1 to the n minus 1 over n to the s. S being a complex variable on a complex plane. So the sum of the alternate divergent series of natural number n square numbers are equal to the Dirichlet eta function evaluated with s equal -1 and s equal -2 respectively. So we're going to use this formula, and a function, the eta function, Dirichlet eta function at m at 1 minus m is equal to 2 to the m minus 1 over m times the mth Bernoulli number for m greater or equal to 1. So for m equal 2 and m equal 3, we obtain the sum from n equal 1 to infinity of -1 to the n minus 1 of the triangular numbers. So it is 1/2 of the sum from n equal 1 to infinity of -1 to the n minus 1 over n to the -2, plus the sum from 1 to infinity of -1 to n minus 1 to over n to the n to the minus 1. So that expression, if we look at it, it is the same as this one for s equal -2. As you can see, if you replace here s equal -2, it gives you that expression. So eta at -2 comes here. Likewise, if you look at this expression and you replace s with -1, eta at -1 gives you that expression, and we plug it here. So now, how do we calculate those one? It's equal to 1/2 of 7/3 of B3 plus 3/2 of B2. Where are those values coming from? 7/3 of B3. So let's evaluate eta at -2. We will use that formula. We need that formula for m equals 3. 1 minus 3 equals -2. So it will be the evaluation of the Dirichlet eta function at -2. M equals 3. 2 to the cube, 8, minus 1, 7, third, B3. 7/3 of B3, here it is. And the eta function at -1, we need to evaluate that expression with m equal 2. 1 minus 2 will be equal to -1, so eta at -1 will be equal to 2 square, so 4 minus 1, 3, half of B2. Here it is, 3/2 of B2. Let's open the toolbox. What are those values? B2 is equal to 1/6 and B3 is equal to 0, the third and fourth Bernoulli number. So let's plug that in. If B3 is equal to 0, 7/3 of B3 of course will be equal to 0. And if B2 is equal to 1/6, 3/2 of 1/6 is equal to 1/4. Alright, so that one is gone and we are left with 1/2 of 1/4, which of course is equal to 1/8. So what we have actually proven here is that the sum of the alternate or alternating divergent series of triangular numbers is equal to 1/8. But we are not after that one. We are after the monotonic version of the divergent series of triangular numbers. So how do we recover from here? Let's write down the expression that linked the Dirichlet eta function with the Riemann zeta function, eta of s and zeta of s. Here it is. And let's evaluate that one for s equal -1 and s equal -2, the same value that we have evaluated previously. So zeta at -1 is equal to, let's plug it here, 2 to the 1 minus minus 1, so 2 square. 1 minus 2 square, 1 minus 4 is equal to -3. We pass it on the other side, -1/3, so we can see zeta at -1 is equal to -1/3 of eta at -1. And then the value of eta at -1, we have it here, we just calculated it, it's here, it's 1/4. 3/2 of B2 is equal to 1/4. We plug it here. So -1/3 of 1/4 is equal to -1/12, which is the value of the Riemann zeta function as -1. Then we do the same at -2. Let's plug it here. 2 to the 1 minus minus 2. So 1 plus 2 equals 3. So 1 minus 2 cube, 1 minus 8, it will be equal to -7. We pass it on the other side, and it will become -1/7 of eta at -2. Eta at -2, what it is, we know, it's 0. We have it here. That's the value which is here. So of course, -1/7 times 0, obviously it's equal to 0. So now we have those two values. We can conclude the sum from n equal 1 of the triangle to infinity of the triangular numbers is equal to 1/2 of the sum from n equal 1 to infinity of 1 over n to the minus 2 plus the sum, the sigma of n equal 1 to infinity of 1 over n to the minus 1. So it is the arithmetic average of the Riemann zeta function evaluated at -2 and -1. We just take the sum and 1/2 of it. We know the values. 0 comes here. This 0 there comes here. The -1/12 comes here. And then, of course, that one is gone. And we are left with 1/2 of -1/12. 1/2 -1/12, which is, of course, -1/24, which is the correct result. We have seen it on the other proof. The correct result for the sum of the monotonic divergent series of triangular numbers. So here it is. We have proven that the sum of the monotonic divergent series of triangular numbers starting from 1 is equal to -1/24. We have been through 7 proofs or 9 proofs. One was inconclusive, one was correct, valid, but incomplete. There is one line that we haven't proven. So we have went through 7 complete proofs and all pointing to the same result, that the sum of that monotonic divergent series of triangular number is equal to -1/24. Thank you for watching.